You guys ready? Okay. Dun, dun, dun. Okay. So, this is too loud, or okay? All right. So plan for today. First, we did the surveys. Good. Check. Then we're going to finish EM algorithm straight through. We had a few good warm-up rounds on EM algorithm, but now we're going to go right through it, talk about a few extensions of EM. And somewhere in there will probably be a break. And then there's a request for a class photo, which I think is a really cool idea. So after the break, could be a class photo. And then after the EM algorithm, we can take some random questions if you guys have any that are still persisting. And or we could just do some brief intro to neural networks. I have some slides for neural networks. And then we'll end a little early, and you guys can pick up your tests. And then tomorrow is meetings with the advisors. And that'll wrap it up. We're good? All right. And well, I'd love to keep talking. All right. So figured you guys would want to review some EM algorithm. So let's remember the setting. We have the latent variable model, in which we have variables, a set of variables that are observed. These are x's, and a set of variables that are unobserved. These are the z's. And we're going to write x and z for z will be all of the unobserved variables called hidden variables or latent variables. X will be all the observed variables. We're going to put them all together in a vector. And we have a probability model. So Pxz given theta will denote the joint probability distribution on x and z. And what we receive is this incomplete data set x. And somehow we need to figure out what this probability distribution, Pxz given theta, is just from x. So in other words, given just x, we want to find the maximum likelihood parameter theta. Okay. Great. So here's the maximum likelihood objective function for this problem. D now is the data we observe, just the x's. We want to find the theta that gives the observed data the maximum likelihood. Okay. So another thing we would like to do, one is estimate the model, let's find theta. And then once we have the model and we're rolling, we observe some x's, that's the unobserved thing. What we want to do is figure out what the z's are, the unobserved part. So in our Gaussian mixture model, for example, x's are the points we observe, and to every x, there corresponds a z, which is the latent variable, which is the cluster that x came from. So given an x, we would want to know a distribution over z, a distribution over the clusters that x came from. So that is what this distribution would be. And this is very easy to calculate. So for Gaussian mixture models, at least, it's easy to calculate. Zi given xi is proportional to the joint of zi xi. And this is very easy to write down. It's the probability of the cluster zi times the likelihood, the Gaussian likelihood of observing xi coming from cluster the distribution associated with cluster zi with the mean mu zi and covariance sigma zi. Is this good review? Any questions on this stuff? Okay. So there's our Gaussian mixture model. The issue is that it's hard to solve this maximization problem, maximizing this marginal likelihood. So what we talked about last time was finding a lower bound for that marginal likelihood, called an L. And it had two parameters. It had a distribution Q and the theta. And we showed that this L was a lower bound for what we want to maximize, which is this likelihood of the data. So let's look at that. Okay. So here was our derivation of this lower bound. The inequality was from Jensen's inequality. So the thing on the left, this is what we want to maximize. It's hard to work with. So we lower bound it by this expression. And if you look at it, you can see that this is an expectation because Q of z, that's a distribution on z. And this expression, this is a function of z, so it's a random variable. This whole thing is an expectation of a logarithm. We call it L of Q theta. Okay? In other contexts, maybe you guys have taken some Probably not. Maybe you've taken a class where you've done variational inference before. L is called the elbow, E-L-B-O. It's a fun term that shows up a lot. E stands for evidence. Sometimes this marginal log likelihood is called the evidence. It's the data you observe. And so that's the E, and the L and the B is the lower bound. So evidence lower bound. I guess the O is part of the bound, BO. Okay, so LQ theta. And remember, the strategy here is to maximize LQ theta over all distributions Q and all parameter values theta. So we're maximizing this lower bound, and as big as we can get LQ theta, whatever theta corresponds to that maximization, that's what we're going to end up with as our proposal for, we think this is the maximum likelihood, or this is our best guess for maximum likelihood. Okay. All right. So the other interesting thing is that we could write this exact expression for the lower bound as the difference of, this is also an expectation. This is the expected complete data log likelihood. Why do I say that? This PXZ, that's the likelihood for the complete data. So X, the unobserved, and Z, the latent variables. And we're summing out over Z. We don't observe Z, so we're summing out over Z with respect to this distribution Q of Z. So it's like we don't observe Z, so we're taking the expectation over what Z could be for some distribution Q. All right. And there's no theta in this second term, so if we wanted to maximize this over theta, we only have to focus on the first term. Okay. All right, and here's the picture. We're going to be looking at this a bunch today. So the red line, that's our, do you guys remember all this, or is this a good review? Okay, good review. Okay. So this is the log of the marginal likelihood. The x-axis is theta, the parameter space. We want to find the theta that maximizes this likelihood of the data that we observe, so that would be something like here, right? This is hard to maximize directly. So we start at some random point theta, some initialization point theta, and we find a lower bound at that point. And the first thing to notice here is that so far only we have to notice that the lower bounds LQ theta, there are a lot of them. For here we've drawn two. So different Q, different probability distribution Q, different probability distributions Q give rise to different lower bounds. So here's one Q gives the blue line, another Q gives the green. Last time there was a question on whether these lower bounds are always concave, right? I was like, I don't want to say that much. So actually, the answer is simple, because there's nothing in the EM algorithm. Well, how do we know if a function is concave? There's one requirement that is even before we start talking about the function to talk about whether a function is concave. This function has to be defined on a set that is convex before we can talk about whether a function is convex or concave. So if a function is defined on a set that looks like, suppose we have a function that's only defined on these disjoint intervals, and maybe where it's defined, it looks convex. But we can't even apply our notion of convexity, because if you take these 2 points and you look at the line between them, I mean, the function's not even defined there. Anyway, in the definition of convex function, the function needs to be defined on a convex set. So here, at parameter space theta, it doesn't even have to be convex. Moreover, it doesn't even have to be continuous. It could be a discrete parameter space theta. So the notion of convexity or concavity doesn't even necessarily even apply. So that's the simplest answer to that question. Okay. All right, any questions so far? Okay, good. All right, so we're going to try to get to the maximum of this marginal log likelihood through an iterative approach. So LQ theta is what we're trying to maximize. It has two parameters, Q and theta, and we're going to do it by coordinate ascent, where we alternate. We'll first fix a theta, then we'll allow Q to vary and find the Q that maximizes LQ theta. We'll call that Q star. Then we're going to keep q star fixed and let the second parameter vary theta and maximize over theta, and we alternate. All right, so that's our big picture EM algorithm. All right. So this is, we start at theta, here's our lower bound. We jump to the maximum of the lower bound, then we find a new lower bound at this point, that's the green line. Then we jump to the maximum of this lower bound, and we continue. Right? That's how that looks. And we're going to look at this picture one more time later to a little bit more carefully. Okay. So this was this amazing equality that we have the marginal log likelihood. And we can write that as equal to the lower bound plus this KL divergence between the distribution Q and the conditional distribution of our unobserved variables given the observed variables. All right. So yes, we've shown that for any Q in theta, LQ theta is a lower bound on PX given theta, what we want. Moreover, here we've derived the exact gap between the two. The gap between the lower bound and the thing we're lower bounding is exactly the KL divergence between this distribution Q and the conditional distribution of Z given X. All right. Okay. So this is the key equality we're going to be using in the next slide, I think. Okay. All right. So let's focus on the stage of theta being fixed. Let's optimize Q. Right. So here's our lower bound. We're at theta old, and we want to find the Q that maximizes this LQ theta. And here's our exact expression for LQ theta. And you'll notice the second piece doesn't have a Q in it. So if we're maximizing over Q, that sure doesn't matter. And here's this negative KL divergence. So what Q would maximize this expression? Yeah, so remember the KL divergence has this property that, first of all, it's always greater than or equal to 0. Second of all, it's only equal to 0 when when it takes two distributions that are equal. Right? So KL divergence takes two parameters. It takes two distributions. And it's kind of like measuring a distance with how different two distributions are, which is, and if the two distributions are exactly the same, and only if they're exactly the same, we get a KL divergence of 0. Right? All right. So this is a negative KL divergence. So what's the largest value a negative KL divergence can take? 0, because KL is always positive. Yes, so the negative is, all right, and then how can we get this to be 0? Sure, take Q equal to P of Z given X and theta old. Okay, so for fixed theta, the maximizing Q, so you'd think this is a very hard problem because, we're maximizing over all probability distributions. Just so happens, in this case, it's easy because we have this property of KL divergence. Okay, so we've found the Q that maximizes L for fixed theta. Okay. So let's plug that in. Plug in the Q star. Then the first term is 0, and we're left with this log px given theta old. Now this is exactly what we're trying to maximize, right? So at theta old, we have equality between what we're trying to maximize and our lower bound. So when the lower bound is exactly equal to what it's lower bounding, that's called a tight lower bound. It's right there. It's tangent to the curve, the function that we're trying to lower bound. So let's look at that as a picture. So that equality is why we have, so at theta old, our lower bound, LQ of theta, it's a lower bound for all theta, but in particular at theta old, it's equal, right? That's that equality that it's touching, that's this equality. That's where that's from, okay? So in the picture, the being tangent is not a coincidence. That's supposed to be there. All right, and everywhere else it's a lower bound. Any questions? Okay. All right, so the general EM algorithm, the first thing is called the expectation step. Why? The first thing is where we find our Q star that's optimizing the lower bound for fixed theta old. We plug it in, so now LQ star of theta, and the next step would be to maximize over theta, right? So but when we write out LQ star theta, let's break it out apart. We have the sum over Q star of this log expression. Now this is an expectation, again, because we're summing out this log expression as a function of z. We've seen the same thing before. Q star of z is the probability of each z. We're summing out over all possible c's. That's an expectation of this log expression with respect to Q star. And we need to compute that expectation to end up with the function LQ star theta, which we'll just call J theta to emphasize the fact that there's no Q involved anymore. We've taken the expectation of, we're only interested in the theta at this point. So that's J theta. So computing this is computing an expectation, and that's why this thing is called the expectation step in the EM algorithm. Okay? All right. So the next thing is we maximize over theta for the fixed Q star, and that's just right this way. And what we're going to need for this EM algorithm to work, as it's stated, is that maximization needs to be doable. Not only that, the expectation needs to be doable. Each of these calculations needs to be fairly straightforward. And when you apply this to Gaussian mixture models, for example, it is. It's straightforward. You can do this quite easily. All right. All right. So let's talk a little bit about what do we know about this thing actually working. So what we've talked about so far is the LQ theta. We're maximizing LQ theta. And how closely can we tie this to maximizing the marginal likelihood, which is what we want, right? So first, let's at least see that we have, for every theta that we move to, we're monotonically increasing the likelihood. So I think this is pretty clear. Every time we take a step, we're moving to a higher point of our lower bound. And the lower bound is always, well, let's just trace it through. So we're starting at theta old, and the key thing that's pushing up our likelihood is the fact that at theta, our lower bound is tight. So we start at theta old, and then when we maximize the blue, we don't necessarily yet know, well, yes, so the red line is always above the blue line, right? So when we move from theta old to theta new, we know already at this point that the value of the likelihood at theta new must be higher than where we just came from. Okay. Then we find a new lower bound that's tangent to the red line. And so again, when we jump to the maximum of this new lower bound here, we know again that the likelihood must also be larger than where we came from. All right. If you don't believe my picture, here's some math. Okay. So for the Q star, we know that at theta old, we have exact equality between the lower bound and the marginal likelihood. All right. Now we're choosing theta new, which maximizes the lower bound for a given Q star. Right? Okay. So the lower bound at Q star and theta new certainly greater than or equal to Q star and theta old, right? Because theta new is chosen to maximize this expression with respect to this theta slot. So this is certainly true by definition of theta new. All right. What next? Now let's start back at the marginal likelihood. So px given theta new. So this is where we ended up. Let's look at what's the marginal likelihood at theta new. Well, we know L is the lower bound. So certainly it's greater than or equal to L at Q star theta new. All right, now we apply this inequality we had above. That's greater than or equal to Q star theta old. And then there we also had equality. All right. All right, so here we see. When we go from theta old to theta new, the marginal likelihood is certainly at least as big. QED. All right. All right, that's one thing. So it's nice that at least as we take steps increasing the lower bound, we know that the marginal likelihood increases. That's comforting. That's good. Let's say a little bit more. Suppose we are able to find the global maximum of the lower bound. All right. So we have LQ theta, and we did a great job of maximizing. We found the global maximum. It's going to turn out that that's also a global maximum of the marginal likelihood, which is fantastic, because that's what we want. So how does that work? All right, suppose Q star theta star is that global maximum of the lower bound. So certainly it's greater than LQ theta everywhere. Okay. And we also know that for the given theta star, Q star, being this conditional probability, is going to be the maximizer. That's what we've shown. So we know what Q star is. All right. So the claim is theta star, which was involved in the maximum of the lower bound, is also the maximizer of this marginal log likelihood. Very interesting. Let's see how that looks. All right. So let's take any theta prime. All right. So this is going to be some other possible theta prime, which could potentially be better than our theta star, and we're going to show that actually it's not. But so let theta prime be any other point. We know that Q prime Z is going to be kind of the best distribution corresponding to theta prime. So the log of the marginal likelihood at theta prime is equal to this lower bound plus the KL divergence. That's always true. Since we're using Q prime, which is the best possible distribution, that's equal to LQ prime theta prime. The KL is 0, right? Clear? Good. So now what? We know Q star theta star, by assumption, is the maximizer of the lower bound. So certainly this is less than or equal to this. All right? And now finally we have the tightness, right? So LQ star theta star is equal to Px given theta star. All right, so if you put it together, we see that for any other theta prime, the marginal log likelihood is going to be less than or equal to the marginal log likelihood at theta star. Okay, so now that's it. 4 lines. Now we've given ourselves pretty good motivation for trying to maximize this lower bound. If we can really maximize the lower bound, we've also found the maximum of the marginal log likelihood. All right. So this is for a global maximum. In fact, in general, we're not going to know how to find the global maximum. Okay, that's too bad. With a little work, you can extend this theorem to local maxima. It's nice. You'll need maybe to have some kind of continuity of your functions or some minor technical conditions, but you can extend to local maxima. But at least this gives pretty good motivation. So there is actually a theorem, not that old actually, on convergence of EM. And it has some technical conditions. It'll go a little bit beyond the level that we've been hitting so far this semester, but I have a reference for you. But just to give you a flavor of what the theorem says. So let's set it up a bit. Theta n, let theta n be our current position for theta in the nth step of the EM algorithm. So after the nth m step. And let's define a transition function m. So if at the beginning we're at theta 0 and after the first round we're at theta 1, and then in general let's let this function m take us from theta 1 to theta 2 or theta n to theta n plus 1. So theta n plus 1 is equal to m of theta n. This will just help us write things down. Is this clear? Yeah. All right. So we're going to assume that this log likelihood function is differentiable. And here's a topic I don't think we've quite mentioned. Let S be the set of stationary points. So stationary point of a function is simply the set of points where the gradient is 0. So when you look for minimum or maximum or saddle points, you're looking for where the gradient is 0. So those are all called stationary points. And it turns out that's going to be the best we can show it, the convergence to a stationary point. Okay. So here's the theorem. So under some regularity conditions, which you can look in this paper for, no matter where you is that funny? It'd be another slide of regularity conditions. For any starting point theta 0, the limit of our sequence of thetas from the EM algorithm converges to theta star for some stationary point. So that's nice. So far we haven't shown that. Until this theorem, we didn't know that we might just run out of steam. We always know that every time we go to a new theta, our log likelihood is increasing. That we've proved. So that's good, but we didn't prove that it will actually reach a stationary point. What if it's always increasing but going slower and slower and slower, and it stops, and it still could go uphill, but it's just like, it doesn't completely stop, but it goes down so slowly it doesn't actually make progress up the hill. So this theorem says, no, that does not happen. We actually converge to a stationary point. So this is a good theorem. It says a few other things, but not so interesting. Okay. Okay, so there's our convergence of EM theorem. Any questions on this EM algorithm stuff? All right. If you guys take the 1005 class, the probabilistic reasoning or graphical models class, this comes up. So certainly. So you could review this when the time comes. Let's talk about a few variations of this EM algorithm to help maybe solidify some concepts. So EM algorithm basically gives us two problems we have to solve, the expectation step and the maximization step. Here's the expectation step, and the maximization step is this simply maximizing over the parameter space. And the thing is, either of these steps could be hard. Right? Computing this expectation could be hard, computing the maximization could be hard. So there's different extensions in each case. So there's something called generalized EM, which is really not such a big deal. Sounds very fancy. But all it is lightening the assumptions on the EM algorithm. So instead of finding the actual maximum of theta in every step, we're content to find some theta new that's strictly better than theta old. Okay? So for example, if you can take a gradient and the gradient's non-zero and the thing's differentiable, you can always take a step, perhaps very small, but you can always take a step where we have strict increase of the function. All right? So this would be generalized EM. Just head in the right direction, even if you can't do the full maximization. All right, it's fine. What else? E step could be difficult. This is very common. When people talk about variational methods, they actually usually have in mind situations where the E step is difficult. And what they do is instead of, so Q star, taking Q star equal to PZ given X, that's the best Q you can take, right? That's where you have equality between what you're lower bounding and your lower bound, right? When you take that Q star. The issue is, where is it? This expectation may be difficult to take for that particular Q star. But the idea is that there might be some other Q star where that expectation is easier to compute. So we've introduced this restriction of probability distributions Q. I'll give you an example in a second. And then you find the Q star that minimizes the KL divergence between these two things, subject to the constraint that Q is in this constrained set of distributions that are easy to work with, right? So we know that we're at least getting the best distribution among those that we're comfortable computing with. So for example, this can sometimes be used for learning in graphical models. Remember we talked about Bayesian networks a few lectures ago? And remember that Bayesian networks have these conditional independence relationships, but also dependencies. That's what the arrows are. They indicate dependencies between the random variables. So a standard set of distributions Q that we consider in that case is called the mean field approximation, is where we consider the set of distributions Q where each of those random variables are independent. So even though they're not independent, we're going to find a lower bound by choosing a distribution Q from the set of distributions where each of those variables are independent. Mean field approximation, very common. All right. Okay, so those are two relaxations. One other application I figured I'd give you because it's very easy, and we talked about map estimates, at least in the homework. So in this case, we have a prior on theta, right? And there we want to find, we're going to still look to estimate theta, but we're going to estimate it by finding the peak of the posterior distribution on theta, right? So in the standard Bayesian setting, we have some prior distribution on our parameter theta. We observe some data x. Now we update our distribution on theta, we get the posterior distribution on theta. So that's p theta given x, distribution of theta given the observation x. And now we could maximize that. over theta. That's called the map estimate, maximum a posteriori estimate. So it turns out we can do the same lower bounding here. Okay. So let's take the same Q star. So LQ star theta, take L to have the same definition. It's still a lower bound on this marginal log likelihood. So here, let me start back up here. So P theta given x, that's the posterior distribution that we're now trying to maximize. Let's take the log of it. And now it breaks up into some pieces. The first piece is the marginal log likelihood, which we just had a whole discussion on how we can maximize this with the EM algorithm. And then we have this extra piece, log of P theta. And then if we're maximizing over theta, this last piece doesn't matter at all, right? Because it's log of px. There's no theta involved. Okay. So we're going to use our lower bound to take care of this piece. So we'll still have LQ star theta. That's how we choose our Q. But the maximization step now has this piece plus log of P theta, because when theta is involved, we need to have both of these pieces for the posterior. So the EM algorithm is very straightforward to adapt to map estimation. Might be worth working through those details as a little summer homework problem for you. Okay. Okay. So that's all I had to say about EM algorithm, actually. The rest of these slides you can look at are, so if we had another homework, what the homework would be derive the EM algorithm for Gaussian mixture models based on this general formulation. So in lecture 13, I think, we talked about with the particular form of the EM algorithm for Gaussian mixture models. It seemed very intuitive, but we didn't derive it. So here's a general derivation of EM algorithm, for which the special case will be, if you work it out, will be exactly what we talked about in previous lecture. So here were some slides giving you the hints that usually come with the homeworks. So you can take a look at. All right. You guys want to start neural networks, or do you want to ask some questions now and take a break and then start neural networks? Questions? Want to get your tests back now? Or at the end? At the end? No. All right, raise your hands if you want it at the end. And if you want it now. And if you want me to mail it to you. Okay. All right, let's do it now. Why not? So we'll do it now, and then we'll let it run into the break. And then we'll start at around 8:10, okay? Should we get going? Oh, do you want to do the picture? Okay. Picture. Up. Would you mind taking a picture? Your screen?
Okay, 27 for that is. 垫桌子上吧。难啊，感觉。这样就。电讲，专业的。他觉得我好高啊。假如别人掉头跳打了一个，转了就下来。我们要被剪掉。我想站在这个桌子上，站，赶上去，跪在桌子上。侧卧，侧卧，踮脚，都是心机。
Again, everybody from this young lady, these guys over you 5 are completely missing.
不是心机婊，把跪在上面。都是心机婊，好多都他妈的心机婊。
All right. How many of you guys know something about neural networks? And, or let me ask first, is anyone taking the neural networks class concurrently this semester? What? There's a okay. All right. So I'll give you my favorite slides. There's too many here to do all right now. I'll flip through the highlights. So I'll assume you guys don't know what neural networks are at all, but I think some of you probably do. So simple goals here are, what's a neural network? At least the simplest kind of neural network. How does it fit into our toolbox? And when should we consider using them, practically speaking? So far, not so far. So far we've done both linear methods and nonlinear methods. The linear ones were support vector machines and ridge regression and lasso. The nonlinear ones are like anything tree-based, random forest, boosting. neural networks fall into the nonlinear, strongly in the nonlinear side of things. The difference between, from a high level, between what neural networks give you and what tree-based algorithms give you in terms of nonlinearity is neural networks are smooth in their output. Right? More recently, they're not always differentiable. Traditionally, they were differentiable, but now they can have kinks, but they're at least continuous. Good pick. All right. Okay. So here's a neural network version of all the linear methods that we've done so far. Theta 1 through theta 1 through 3, these would be like our feature vector, represented now as, so this diagram is not Bayesian network, it's another kind of diagram, more like a computation graph. But theta 1, theta x1 through theta x3, these are like 3 features as input. And what this represents is each of these features getting multiplied by some weight w. Each of these arrows has a weight along it. And they all come together into a final node, which in this type of diagram, it means that they're summed up. So score is equal to, in linear algebra notation, w transpose phi of x. If phi of x is the vector of these 3 nodes, w represents all of these weights. So this would be a way to represent a linear classifier in the neural network notation. So of course, it only gets exciting when we add another layer and a nonlinear transformation. So what has happened here is we add in an extra layer called a hidden layer between the input layer and the score, the final output. And the input to each of these nodes comes from the entire feature vector. And so this feature vector is, each of these entries are multiplied by a weight, in this case v. And then they're added together, and that becomes the input to this node. And then that sum, that linear combination of the feature, is passed through some nonlinear transformation, sigma. That's what makes these neural networks nonlinear. And the same thing happens at this other node. The difference between these 2 nodes is that the weights, the linear combination of the input, is different for each of these 2 nodes. And then finally, the output of these 2 nodes are linearly combined into a final score. This is kind of the template for a basic feed-forward neural network. Any questions on that? Is that clear?
Yeah. Which part is nonlinear?
Okay. So here's let me write down the math for what this picture means. So a hidden node, let's say h1 or hi. It's the output from the hidden node, what travels down this arrow, is equal to sigma of, sigma, this is a function, it's called the activation function. It's generally nonlinear, and we'll look at some examples later. So that's where the nonlinearity comes. And what you pass into that nonlinear function is a single number, a single scalar, which is a linear combination of the input. All right? So to summarize, you get an x, you take your feature representation of the x, that's phi of x. You take a linear combination of that feature vector, that's v transpose phi, that's a scalar, a number. You pass that through a nonlinear function, which gives you another number, and that's the output from h1. You do the same thing on h2, you get 2 numbers, and then you take a linear combination of those 2 numbers, h1 and h2. All right. If you put it, yeah, go ahead.
Operational functions are the same for each hi?
You can do what you want, but generally, yes, the activation function is the same for all the nodes, typically, yeah. Well, yes. You can have any number of hidden nodes, you can have any number of layers. This is this basic template. So, I'll see. These are the bullets to answer your questions. So, yeah, there could be, 50,000 nodes. There could be, traditionally, if you go back 10 plus years, there are usually like 1 hidden layer. But more recently, you go back 10 years and they're doing like 8 layers. And most recently, they're doing like 1,000 layers. So there's been this, the reason they weren't doing more layers is because they found them hard to do training on. The learning part was hard with deep networks. But there's been a lot of advances in recent years on how to effectively learn all the parameters. So all the W's and the V's are learned from data. And Nothing too fancy, just basically stochastic gradient descent, maybe some minor variations and improvements on that, but they've had difficulty training them for smaller networks, but now through different developments, they can train them even for networks that are like 1,000 layers. So. The same. No, I mean, the first input layer is not hidden, and the last one is not hidden. The rest are, because you don't have a direct observation of these nodes. Okay. The difference between, the reason these aren't, in latent variable models, like the EM algorithm we're talking about, we actually wanted to know the values of those hidden nodes. Here, we don't really necessarily care about them. They're just a way to get us this nonlinear function. So the way I think about this is a parameterized nonlinear function. The parameters are all the w's and all the v's. We have to learn them. But from a high level, nothing is unfamiliar to us here. This is a set of functions mapping from R3 to R in this case. And they're parameterized by a w vector and a v vector, and that's about it. Yeah? Okay, so how does this compare to linear regression with nonlinear kernel? So let's just call it a nonlinear feature map, right? Okay, so that's just simply back to this case. So we put our nonlinear features as input, and then this is linear regression. So this is something really new, right? Even if we have the input is nonlinear, is represented with nonlinear features, even so the function is a nonlinear function of that. Okay. So this is really different. Yeah. Oh, yeah. Why do nonlinear? Well, I think the simplest motivation is that it's hard to invent all the nonlinear. If you wanted to do it without this, then you would have to invent your nonlinear features. And, well, people have been doing this for a long time, but if you could have it learned automatically, wouldn't that be better? And in fact, in recent times, performance is a lot better in certain domains. So. Yeah.
How do we predict like who decides sigma?
Sigma is chosen. Sigma is not learned in this case. Sigma is chosen by the data scientist. There are just a few that are typically used, and I'll show you those in a minute. Yeah. Yeah.
Can we consider the age as the kind of new feature?
Oh, can we consider the H's as new features? Absolutely. I would like you to consider H's as new features, in fact. I'd like you to consider H's as features that were learned by the neural network, as opposed to having to have designed them yourself.
So we can have more, in this example, we can have more age than more signal. And we also can have less features.
You said you can have more,
Yeah.
you can have more, yes. Instead of H1 through H2, it could be H1 through H1000. Yes, and you can also have more layers. That's right.
And under what condition we want to increase the features?
That's a great question. So under what conditions would you want to have? So you have how wide the network is and how deep the network is. That's a good question. What people are finding recently is that deeper networks seem to work better if you can train them. So if with all the tricks of the trade to be able to successfully minimize your objective function well and actually get good training error, it seems that deeper networks tend to work better in terms of, say, less overfitting than wider networks. Say even for the same number of nodes. But it's a little, it's still very much an art.
The deeper network give better performance.
People are finding deeper networks tend to be giving better performance, at least in certain domains, like vision, for example.
And the wider gives overview.
No, I don't want to give rules. I'm just saying very loosely speaking that people have been having success by making their networks deeper more recently. So this is a good direction to go. Yeah. So one of the challenges of neural networks is there's so many things you can vary. The structure of the network, your activation function. You have all the usual problems of how do you do the optimization, your step sizes, and these sorts of things. So there's a lot of stuff going on in neural networks. So it seems like everything just works. You go to a neural networks conference, I just came back from one, and there's all these cool things that work really well. And you get the feeling that like, oh, I'll just try it and it'll work. And the thing is that there's all these minor variations on what works that don't work at all. So you'll talk to the people and they'll be like, yeah, this was great, but when I changed my activation function to this other thing, it actually was very poor. So I guess if you're going to get into neural networks, a good idea is to kind of start with something that you know works and then gradually tweak it to a direction you want to go, unless you have a lot of time to really do a lot of experimentation to get it working. But the cool thing about the neural network community these days is that, boy, they put all their code on GitHub, and they are really into sharing and having everything be reproducible. So in some sense, it couldn't be easier to get involved. To like, state-of-the-art stuff is out there, and you can reproduce the results. Then you want to play with it. You can always go back to the settings they had that worked. So it's a good field for people who like to play around with stuff. And it's not as good a field if you like to have very rigorous reasons to have certain parameter settings for your neural networks, because that still does not exist to my knowledge. So it's a lot of playing and tweaking and experimenting. The results also tend to be state-of-the-art in a lot of areas. So it's a good era for tinkerers. Mathematicians maybe already had their day. Okay. All right, any more questions on this basic setup? All right, so activation functions. This was the most common for many years. It's called sigmoid. Saturates at 0 and 1. There's some arctangent, which is basically the exact same shape, just shifted to goes between -1 and 1. That's sometimes used as well. The key piece is that it's be nonlinear. That's what gives the neural network its power, its magic. If it were linear, it wouldn't be interesting at all. It would just be all these layers of linear transformations would collapse to a single linear transformation, and that would not be anything new. All right, so that's a sigmoid. Here's the one that's become very popular recently and works very well. It's called a rectified linear function. Now people just refer to it as ReLU, for R-E-L-U. This is the shape. So do you guys see some pros and cons of this type of function? Imagine you're dealing with it. You write down your objective. It's got this function in it. You're going to do SGD. You're going to take gradients. You're going to have to compute with it. So this piece is constant at 0. This piece is just y equals x. Yeah, so an issue is it's not differentiable. But OK, we're OK with that. We do subgradient, no big deal. You never hit the kink anyway. OK, we're OK. So the other thing is that it's two things. It's super fast to compute compared to, here we have an exponentiation. Yeah, computers are fast, but exponentiation is still, you have to do a bunch of operations to compute the exponential of a number. But this is dead easy. It's an if. There's no faster computer computation that I know of than an if. So you branch if it's less than 0, and it's either the return is the same as the input or it's 0. So this is very fast to compute, and its derivative is dead easy too. It's either 0 or 1. Okay, another if statement. So one major thing you gain here is computation speed, why is that important? Because if you're tweaking your model a lot of ways, you want things to run fast, you can tweak more. Common theme. You want to use a fast computer and a fast algorithm primarily to give yourself more time to tune hyperparameters, because a lot of your performance, not just for neural networks, but for all models, is going to come from carefully trying out new things. You try out new features, you try out new hyperparameters, you try out new models. So speed is important. All right. OK. So I thought this was neat, a little bit of a look inside a neural network. So here what we're looking at is fitting a function y equals f is x squared. F of x is x squared. So this represents the function that we're fitting. The blue dots are our training set. And these other graphs are the outputs of 3 hidden nodes. So imagine we have this network, except instead of H1 and H2, it's H1, H2, and H3. And what we're looking at is the output of 3 hidden nodes across the input dimension is 1, so we have 1 input node. Input dimension is just a real value. And we're looking at the output of those 3 hidden nodes for various values of the input. And these are the curves that we get as the hidden node outputs. So we see that nonlinearity is present in the output of the hidden layers. And then the red line is the final linear combination, which exactly nails this x squared. So it's pretty neat how these functions are combined to fit what we're after. Is this clear what this is? So I have the same picture for a few other functions. Sine x, these 3 outputs add up to linearly combine to sine x. That's pretty cool. Here's a v function. So it's not quite as precise because this is for sigmoid logistic activation. It's very smooth. So to get a kink, you got to work kind of hard. So that's why the sigmoid has to change very quickly. OK. Here's a step function. Cool. Yeah, I thought it was cool too. There's a great, there's this great JavaScript kind of lab simulator where you can make networks like point and click, extremely easy. I'll send out a link to Piazza. It's a great way to get a feel for what's happening, to get pictures like this. All right. So, yeah, question?
Are these pictures made experimentally, or there is you keep the sigmoidal function in the outputs of the edge?
All right. So what happened here is we trained the model using stochastic gradient descent. I didn't talk about loss functions yet or how, but it's nothing surprising. And all the weights are set. Then we feed in different values of x as input, and we look at the outputs of each of the hidden variables. So now, again, your question?
I just wanted to know, all these things, the these and the edge, where you tried, you made we use this function, what we named as reload. So was it experimental, or is it it has a we did it because this was the thing, or it was just experimented to use this?
Oh, yes. So the choice of what activation function you use that's a modeling choice. So you try sigmoid, you're like, I didn't like that one. Let's try relu. Let's try. There's not that many choices that people use. So you try one, you try the other, and that's it. More or less. There's some, more recently, there's different modifications of relu.
Is there any motivation using one function versus the other function?
Well, I gave you one strong motivation already, speed and ease of computation. But you're asking, I think, from a modeling side of things. Well, one thing you'll notice about relu is that it's unbounded, right? Whereas the sigmoid is bounded between 0 and 1. So what happens is if you look at predictions outside of the area where you had training data, the behavior is kind of predictable, which is that relus tend to go off like that, and the sigmoids don't. So, yeah, walk like an Egyptian. Okay. All right. So, okay, any more questions on this? I want to show you just a few more things, yeah.
Have people try just to bounce the value at some output?
Yeah. So like, that's a good, so I've seen that in not neural networks. I've seen that in like an SVM setting. And I'm almost certain it's been done in neural networks. I just don't know. what's going on with that. I don't hear it talked about a lot, so it somehow wasn't so amazing that it became mainstream. But yeah, I'm sure that's a feasible thing to do. The issue, well, there's a bit of an issue. So if I understand correctly, you want to truncate the. So the problem is, if you are at the past the truncation, and so you're at the level flat part, then you will get no gradient update. So as you do gradient descent, you have no change signal when you're in the flat part. So this is an issue.
Isn't that the same as the lower part?
Yeah, so, right, so if you get too far negative, you're in trouble for a ReLU, but this would make it in trouble also if you're too far positive, so you're kind of padding both sides, you know? Okay, so it's a cartoon diagram of the type of thing that you get these days when you do a neural network for vision, or what you hope to get, and you actually do find, is that if the raw input is pixels, okay, that's your input, what you'll find is that at different layers of your network, you get hidden nodes that tend to respond to different types of patterns in the input. So for example, this particular, what's going on here? This particular cute block corresponds to a hidden node of the first layer of our neural network. And one way to interpret this is that if the pixels in the image kind of have high inner product with this filter in a particular region, then this hidden node will have high output, and otherwise it will have low output. And so these are the types of patterns in the input that each of these hidden nodes respond to. So you can see at the lowest level, they'll respond to kind of, these are going to be like edges. And at a higher level, many layers up, if this is a face recognition problem, it tends to learn to respond to certain face parts, so noses and eyes and stuff. Or at the top level, it'll even be like whole faces. So more generically, you're expecting your learned features to become kind of to move from very low level, simple features to more complicated features at the high end. So for instance, there's kind of this theory in neuroscience, or hypothesis, that you'll have a neuron in your brain that responds when you're looking at your grandmother. It's called the grandmother neuron, okay? There's like this one neuron that starts firing when you see your grandmother. So in fact, for neural networks trained in this way, they can often find the analog of a grandmother neuron. So neuron that will respond to a particular, this one responds to cats, this one responds to dogs, this responds to your best friend. So they find that happens sometimes. Very interesting. Yeah?
A question about the complexity of a neural network. The complexity is defined as number of hidden layers.
Great question. So how complex is our neural network, and why do we care about this? Because it has to do with overfitting and the trade-off between estimation error and approximation error. So let me jump to that. Neural networks. Let's think of it as a hypothesis space, right? So what are the hyperparameters? Yes, it's what you said. Number of layers, number of nodes in each hidden layer, the activation functions we choose. So, and yes, our set of functions, our set of neural networks are parameterized by these things, and the size of the complexity of the hypothesis space will grow or shrink depending on these parameters. There's one thing that makes the story a bit more complicated, though, which is that, when we spoke at the beginning of the semester about like L1 and L2 regularization, we had this, first we talked about balls in feature space, right? Like an L2 ball in the feature space, where we're going to limit ourselves to all prediction functions that have L2 norm less than alpha. And that's clearly less complex, less likely to overfit than all functions with L2 norm of the parameters less than 2 alpha, right? So that was very clean. And then, but in practice, we are doing this other form where we penalize by alpha times the norm, right? But we argued that actually you could still picture the ball thing because there's a homework assignment where we proved the equivalence of those two forms of regularization. So if you have this penalty function form, it was equivalent to the kind of bounded norm form. And so it's fine that if you're picturing like your ball is getting bigger or smaller, changing the complexity. Okay. And also, when we go to minimize our objective function, we tend to find the actual minimizer because we are almost always talking about convex functions. So we either get very close to or the actual minimizer. Okay, so neural network hypothesis space. So I have a separate slide on it, but I will just tell you now that neural network objective functions are not convex. And this is why people avoided them for a long time, because they were hard to minimize. And from a math side, if you wanted to prove theorems, you didn't know what to prove because you wanted to prove things about, what you maybe could prove something about is the global minimizer, but you'll never find it. So what you have to prove something about is where your algorithm ends up, and that's a very hard thing to get a handle of. Anyway, so because this thing is not convex and potentially a very complicated model, there's all sorts of tricks or techniques that people use to not overfit. All right. So things like early stopping, we know. You stop when your validation error starts going up, that we know. But there's these other things. I'll just flip through. So yes, we could do L2 and regularization, L1 regularization on a neural network. That's fine. But there's these other strange things that people come up with, like dropout. This is where, as you're learning your network, you randomly select some nodes to kind of zero out and not allow them to participate. Seems like a funny thing, but it seems to help prevent overfitting quite a bit. So other things about where, well, because it's not convex, where we end up is determined highly by where we start. So you pick a starting point, and you maybe end up in this little local minimum, but if you started somewhere else, you'd end up in another local minimum. Okay, so the point is that for neural networks, it's harder to get it's not as clear a trade-off between a big network leading to overfitting. This is what I'm trying to get at. So for most other things, it's a very clear connection between small is, we want something as small as possible, it still fits the data. But it's not so clear that's the case for neural networks. In fact, people are finding that sometimes bigger networks perform better in out-of-sample performance, even if you could get the same training error with a smaller network, which is like the complete opposite of what you would normally get. And what I'm suggesting is that the reason is because there's all sorts of trickiness in training a neural network that are used so that you don't overfit, and are used because it's not convex, which makes it a less clear connection. Okay. All right. So here's one cool thing you can do with neural networks, which is you can have more than one output node. You can have multiple outputs. And this is a very easy way to get what's called multitask learning. This is where you'd have an input for which you want to predict multiple things. So here's a simple example. I have two binary classification problems that I want to apply to the same input image. I want to know, is there a cat in the picture, yes or no? I also want to know, is there a dog in the picture, yes or no? Okay, we could denote that with two separate outputs. And I mean, how do we train? We still need a single objective function. Okay, we'll just look at the loss of this output, add it or something to the loss of this other output, and then train accordingly. So one other term I wanted you guys to hear about. So the objective function is exactly what you'd expect. You have your prediction function, which gives you a score, and then you could write down a loss function. In this case, I wrote down square loss. And the first approach to minimizing this objective function is stochastic gradient descent, or mini-batch gradient descent. This is kind of the stock approach used in neural networks these days. And there's also this thing called backpropagation. Have you guys heard of backpropagation? So backpropagation is actually nothing but a very efficient and clever algorithm for doing gradient descent. In fact, for computing the gradient of your function as well as computing the scores of your neural networks. So it's kind of a forward pass to the neural network where you compute the output given the input, and a backward pass where you compute the gradient with respect to that example. Gradient on that example with respect to the parameters. So I want you to compartmentalize backpropagation and say to yourself, okay, backpropagation is just a clever algorithm for doing gradient descent for neural networks. Conceptually, it's, from a modeling math point of view, it's nothing new at all. It is a cool algorithm worth a look at some point. Okay. So multitask learning. Okay. All right. So the last point I'll make about neural networks is that, so we've already mentioned that you could think of the hidden layers as features that were discovered by the neural network. So there's this thing called overfeed. Some of you guys are probably using it. So they've trained this neural network on a huge amount of data, image classification data. This ImageNet data set. And they had a very successful neural network. Took an enormous amount of computing power and money to train the network. And what they've done is they've stored the hidden nodes, which you can consider as features that were learned by the network. And you can now download these features to you. So they're already learned, so you can just download the program to compute the features on a new image, and then feed those features into a simpler model like whatever, SVM, for example. So that's a nice ability to reuse all that computational power that someone already invested to generate this network. And maybe they're predicting, they may be predicting a fixed set of classes, so you don't really want their whole network if you want to predict on another set of classes. Maybe they're predicting animals, but you want to predict car type. Turns out the features, a lot of those features that were useful for one type of image problem, empirically, tend to be useful for other image problems, even if it's different classes or different domain. So this is this could be known as transfer learning, where you transfer some learning that was done in one domain to another domain. So you just take those features, and you could immediately plug in those features on your new data set, and it trains up very well. Have you heard of word-to-vec? Word-to-vec is the exact same idea for words. So word-to-vec has a training set. Talk about that in another class, which I recommend to you guys. And they come up with a representation of every word that turns out to be very useful on new domains that you can use instead of bag of words. Okay. All right. Very good. Okay. So here's just a little picture that kind of gives a nice perspective on what neural networks mean to us these days. And it seems that as the amount of data we have increases dramatically, the performance of most of the algorithms we've spoken about, at least the neural networks folk claim that they level off. The performance levels off eventually with a certain amount of data, whereas the deep learning has so much capacity, because you could always make this network larger and larger, tends to keep getting better in performance as you feed it more data. Of course, it takes tremendous amounts of computation time to do. Okay, so that's what I had to say about neural networks. Any questions on neural networks? I just wanted to give a few pointers at the end to other classes you guys can take. Yeah? Yeah, deep learning is about neural networks, and the deep refers to lots of layers. That's right. That's it. Simple as that. Yeah.
With regards to the fields, we've seen for image recognition, video or audio, they're using neural
Yeah, for machine vision and speech recognition, neural networks are definitely state of the art. All of them are, all state of art methods use neural networks. Natural language processing is very interesting and coming along. Is that your question?
No, the question is which would be like different problems we should try to approach with neural nets, and which is there.
Oh, thanks. Good question. Yes. Okay. So if you want to do a serious job on vision, neural networks, convolutional networks. If you want to get in speech recognition, neural networks for sure. If you want to do some kind of document classification or something, go ahead and try a word-to-vec or something to represent. Generically speaking, if you want to use neural networks, you're thinking about, you have a ton of data and you have very powerful computers to work on those data, and primarily that means GPUs. So graphic processing units are what you need to make progress on neural network training these days, it seems. You're not using when you have less data, and yeah, I think, yeah, I would say that, yeah.
But once they're trained classification, or I mean prediction is not, it doesn't take that much.
Prediction is still slower because you got more layers to compute, but yeah, it's not, yeah, it's not as bad. Yeah.
I'd like some example that, at least for NLPs, if you have one hidden layer or more hidden layers, it's equivalent.
Yes.
What does change for other models? Like, what's the biggest change to NLPs? Why does it improve and why make more hidden layers simple?
All right, good question. So there's a theorem which says that all you need is one hidden layer, and you can represent any function arbitrarily closely. So in terms of approximation error, there's no limit to how well we can do with just a single hidden layer. The issue is we'll potentially need exponentially many nodes on the hidden layer. So when you have more depth, what you potentially get is a more efficient representation of your function. And by efficient, I mean fewer parameters. I mean fewer nodes. Okay. So that's what you gain from depth.
Even for NLPs?
MLP meaning multi-layer perceptron? Yes, that's all we talked about. Yeah. So another term for this neural network structure is multi-layer perceptron, even though it has nothing to do with perceptron. Yeah.
In this network, we know the score. We know why, so we compute the V and W. And in some unsupervised questions, we don't know the why. Can we apply this kind of method?
Question is, can we apply neural networks to unsupervised learning? So we only have X's and no Y's. Yes. Okay. So there's one really cool way, which is called an autoencoder. An autoencoder, A-U-T-O, like automobile, but autoencoder. And here what you do is you take your input, and you have a network, and you have a bunch of layers, and you have this thin layer called a bottleneck, and then you have layers that get bigger again. And you try to predict the input as output. So you get an input, and you feed it through your network, and at the output, your loss is how far off your output scores are from your inputs. So, so if you can reproduce the output well from the input, but you stuffed all that knowledge down and passed it through a bottleneck of very few nodes, the idea is that you've done some good knowledge compression, and that somehow the network has discovered some good representation of the input space, and this is one way to kind of learn unsupervised. There's other ways to train them unsupervised, but that's totally different than what we've done before. Yeah. Okay, last question because we're out of time.
What's your favorite part teaching this class?
What? My favorite part of teaching this class? Oh, I like writing the homeworks. No, my favorite part really is when you guys ask questions and participate, and there's some give and take. That's what makes it a lot of fun. So on that note, it's been a really fun semester. I want to thank you guys for being a great class, and lots of luck coming forward for you guys.